So I was here before COVID, the summer before COVID, and back then life was quite different. COVID made me realize that I want to be able to solve problems when they start to happen, and in those settings, you don't have a lot of data. So at that point on, I moved to self-supervised learning foundation models, which will be the focus of my talk, and now that's basically most of my research. To give you a little bit of context, we need to click on something, I think. To give you a little bit of, should I click on this? Okay, perfect. So to give you a little bit of high-level context for those of you who, I'm sure everybody knows about it, but just to put it in the context, up until 2017 or so, our field was in the era of supervised learning, meaning that we took large data sets and they would come with labels, and we would train more and more advanced models, advanced architectures, for imaging, if you remember, okay, there is inception, ResNet, etc. Then natural language processing, like attention models, etc. In 2017 came one paper called Transformers, Attention is All You Need, which made a lot of news in natural language processing only, nothing else. And that was the beginning of very large models, which were trained on unlabeled data. Like they would be hundreds of millions of parameters. And to feed those parameters, the Google researchers actually developed methods to train these things in an unsupervised way. Or let's call it self-supervised, because we built pseudo-labels out of the unlabeled data. And then a couple of years, like those models basically took over the entire field of NLP. Everybody else was like, hey, wait a minute, what's going on there? So eventually in 2022-ish, computer vision also managed to extend their approaches to transformer models. They're all on the basis of self-supervised learning and pre-training models in an unsupervised way prior to your application. And let's call those few years the era of self-supervised learning. Now that era has matured into what we call foundation model era, which means that if you see most of the big labs, they release these big models that are pre-trained in a general purpose way. It could be like, large language models. It could be large segmentation models like Segment Anything, SAM. It could be a lot of imaging models. They release this, and then different other people can take these and fine-tune them. So now we are in this era where I think that's where it is going. And kind of, I guess, in parallel to that, let me point you up there in healthcare. So yeah, COVID happened 2020, right? And then that also was a good reminder for a lot of us that, okay, when a real crisis happens, initially you're not going to have millions of data points. And that initial month is the point where there's a lot of uncertainty. That's where AI can help. So how can we move to that era? So that combined with all the development is why I personally, in my lab, I completely focus now on self-supervised pre-training of large models, but also I think the field is moving towards that. So in this talk, I'm just giving you a little bit of overview of all of this, and I give you a little bit of justification that healthcare is a data-rich domain. We can actually build really large models. We can be very ambitious. Then I will dive into a couple of examples in terms of multimodal. Healthcare is very diverse. You have imaging, all sorts of imaging, 2D, 3D, large images, small images, and then you have electronic health records, which are like these tabular kind of things. You have ticks, how do you handle this? And then as maybe some of you attended the diversity in AI, so as these models get developed, if your data set is unbalanced, like it's majority, certain ethnicity or certain city or country represented, how would you ensure that the other minorities are actually learned? Like you have this foundation model, it's been trained on this massive data, and it goes everywhere. It's shared across, and everybody uses it. How do you make sure that that model is actually good enough for all these other smaller minorities, right? So that's kind of fairness that we address. I'll try to talk to that, and then I will close it with some thoughts on multimodal learning. So I will kind of skip most of this, but just at a high level, 2017-18 is where we see a paradigm shift in terms of size of the models. When your model gets orders of magnitudes much larger, you need more data to train this. That's kind of why supervised learning no longer was enough. We switched to utilizing lots of unlabeled data sets to try to solve our problems. It's really good fit for healthcare because usually, first of all, there are a lot of undiagnosed conditions, which means that the data is there. It wasn't labeled yet. So in that case, it's good to be able to train a lot of things without relying on that label. That's one aspect. And then the other aspect is that for a lot of like smaller and more like rarer diseases like pancreatic cancer, you may not have a lot of pancreatic cancer data sets, but you have a lot of general population data sets to learn a lot of parameters of your model. So that's kind of the foundation model overview, and this is a transformer paper that made a lot of differences. And the follow-up to that was, let me give you a little bit of, just a BERT and GPT, all of those were follow-up for this one. It's based on self-attention. It's multi-dimensional. It's much larger models. The concept of self-attention, for those of you, I'm sure everybody basically knows, just a review. Self-attention, sorry, this GIF doesn't work. I've sent a PDF. But the other side, self-attention, is like you have your sequence of tokens. They can be anything. They can be image patches. They can be words in a sentence. They can be EHR elements. And you repeatedly update the representation of that token by trying to understand if there are some other tokens, other patches in your input that relate to it, and then update the information based on these neighborhood information that you have. Everything would be learnable. That's the main concept of self-attention. This is the core of this paper that took over the world, basically, in 2017. And so far, there's been a lot of research in this architecture. And then, 2018, a more general purpose version of it was released, which is basically a lot of core for what we do. When I would talk a little bit about self-supervised learning, but when we talk about self-supervised learning, it means that you have some kind of pseudo-labels. You kind of mask some part of your input, and you try to predict it, and then that makes the model try to understand the concepts. Okay, that's a very high level. This is what the transformer model is. A lot of like layers here, self-attention, etc. But the input is, a sentence, a token sequence. You mask some of them, some words in there, and then you just ask the network to predict it. And by doing this over trillion-sized data sets, your model actually gets quite a bit of the training, and then you just need a tiny data set later, or maybe even few-shot learning in terms of like GPT models or ChatGPT, etc. It's even prompting, which means you no longer even need observation to try to use these models. But there's a lot of strengths to this. Vision transformer is some similar concept. Just to explain to you, you turn an image into a bunch of patches, okay? And then in the original model, you don't even have convolution anymore. It's crazy. Like I'm thinking about an imaging model without convolution, you project them linearly into some representations, and then the rest is the standard transformer that was done. Okay, so that's vision transformer. So this architecture, as a high level for you, has been now the basis of a lot of more recent advanced models that are released. And so it's quite interesting. And if you look at the timeline of development of models as you go up, in terms of the image classification, you have the performances, and then you have different, what is the methods that are at the core of these approaches. And recently, all of these methods are both in NLP, in computer vision, natural language processing, basically. In most of the domains are now these self-attention models trained through unsupervised setting. Okay, so that's where we are. These models are getting bigger and bigger and bigger, which means you need more data and more settings to train them. And the only way to get enough data to train them is through unsupervised learning. Okay, so this type of unsupervised learning I was talking about is called self-supervised learning. It's currently the most successful approach in unsupervised learning. It might not be the only way, but that is the one that actually managed to work so far very well. What is self-supervised learning? Self-supervised learning means you actually build pseudo-labels out of a bunch of data sets. If you have images, you can blank out some part of the image and try to predict it. The ideas have been there, just it managed to actually get it to use. And then if you have a text, you mask some of it. If you have electronic health records, you mask part of it, and you try to ask the network to predict that. By doing that, you actually learn most of the way of the learning is done, and then you just need a little bit of more data to fine-tune them. Unlike supervised learning, which as your modality gets larger and larger, self-supervised learning actually is the approach that scales well if you know more about some, let's say, patient, right? In the original setting, if I had an MRI data set and I had an EHR data set, if I would concatenate these representations, my dimensionality of the model would go higher, so I would actually need more data to be able to train multimodal settings. But in self-supervised learning, you can mask EHR part and combine them with imaging and ask the imaging part to predict this. So because you leverage the correspondences within the data, this approach actually scales with multimodal data sets, which is the real world, okay? If you start to dig into the applications, almost every domain has multimodality. That's finally some approach that works with multimodality, okay? So, and also in computer vision, something I will mention to you is self-supervised learning is also developed not only through self-attention models and transformer, but also some approach called contrastive learning, which means you get one image, let's say one image, you don't know what it is in it, you just augment it in two different ways, and then you send it to the network, and you expect the network to have similar representations, to be robust to this augmentation. You want the representation at the end for the network to not change so much how you add noise to this. For example, all of these images over here, our brain tell us, okay, yeah, they are the same image. Okay, we don't even know if it's a dog or whatever. We just say, okay, these are the same images, I can tell. So you kind of want the network to leverage that. That's contrastive learning. There's a lot of literature in that domain in computer vision. Contrastive learning in computer vision is, at the moment, hand in hand with the masked pre-training in the attention approach. Okay, so that's the state of the art. And then, so a lot of the approaches up here are contrastive learning. Then in the bottom is the transformer-based approaches. They're relatively comparable at the moment, okay? Now let's look at the healthcare data landscape. So when you look at some of these open source models that were released, you kind of see, okay, how many billion tokens or items were in them when they were released. And then I give you an example of NYU data, okay? NYU is it's a big hospital in a big city. We have a lot of data. I understand everywhere is not the same, but that said, there are a lot of opportunities for federated learning. So the data is there in the healthcare field, and we can leverage it to build foundation models comparable to the level of like GPT, etc., which really are very powerful. So at NYU, we have had 11 million patients so far every year. This data grows. That's a lot of rich multimodal data set. You see some examples of the imaging sizes in what we have. And there are a lot of initiatives that are collecting data in publicly available settings for various diseases. So there is a lot of hundreds of billions of tokens also in healthcare. Okay, so from data point of view, we are comparable. We can be ambitious. We can build serious big models. We can open source them so everybody in the field can move on. And so that's kind of, I guess, and the richness of medical data is that it's very diverse. So if you go to departments of radiology, radiology is imaging, right? So you have so many different types of images. Some of them are very large, like X-rays are very high resolution. They are big images. Then you have MRI, which is usually 3D. Then you have like PET imaging, it could be videos, very diverse settings there. And then you could also have histopathology imaging for cancer. Like it's kind of like almost like specialty related in terms of types of the data that it captures. Radiology, then histopathology has its own images. They're under microscopes. There are tens of thousands of pixels each direction. How do you handle them? It's its own challenges. Then you have EHR data. EHR is like lots of big CSV files. Okay, we're talking about 500,000 dimension. If you open them up, it kind of tells you indicators and things like that about at different time point, like they're all timestamped. What happens, like what are the diseases that the patient had? So diseases could be like the dimension of 80,000 dimensions. Okay, it's not like if you do one hot encoding, what happened here and there, 80,000 possible diseases, a similar scale of medications, etc. That's EHR data, and then you have clinical notes as well, which could be different languages. In Norway, they were probably Norwegian, right? So you want to think about how do you develop things that can work with the clinical data in the text setting. So with that basic, I guess, overview, let's dive into a couple of settings. First, I'll talk a little bit about, so I guess, at the high level, there's a lot of unsolved challenges in developing these models in the setting of healthcare and also in general. There are a lot of unsolved challenges in methods of self-supervised learning. So I'm going to give you some flavor of trying to tackle these challenges one by one, and then, hopefully as a field we push this direction forward. So I will talk about a little bit on the imaging domains. Very briefly, I'll talk fast, and then a little bit about how we focus on electronic health records, which is a different modality, not very well studied. And then another study about fairness, which they're all concerns of mine. They're all going to come together in a multimodal setting, which I will tell you later. So on the medical imaging, let me keep track of time as well. So I will be very fast on these. I will share two studies, okay? One study, the first one, is about improving self-supervised learning for medical imaging, trying to squeeze as much signal as possible from a data set that may not be as large as, it may be like NYU scale data set, but it may not be internet scale data set yet. How do you still squeeze more signal during the learning, right? So that's the first one, and the second one is an application of self-supervised learning to histopathology, just conveying that you actually need to be thoughtful and solve specific challenges related to your own task. In this case, I'd say histopathology imaging, to try to solve unsolved problems. Right, so very briefly, the first one is with two of my brilliant students who have both now graduated. Our focus was on some data sets you can see about its general purpose. The focus is methodology, and it's about improving, basically leveraging intermediate layers. Let me go back a little bit. Intermediate layers during the self-supervision. Normally, if you remember, I'll go forward. If you remember, it's kind of like the same. You can see here, like you augment the image in two different ways in contrastive learning, and then you try to bring these representations closer together. There's one variant of contrastive learning called MOCO V2. It's just a lot of adjustments to this approach that are a little bit more computationally efficient, are good for large images, which is common for healthcare. So if you have these ones, what we normally you bring the representation at the very last layer closer to each other, but we already know that semantically, intermediate layers, the semantic starts to emerge, even not only on the very last layer, but like a little bit before that, the concepts are there. So we actually say, hey, what would happen if you also encourage intermediate layers to also be robust to data augmentation? And would that add you additional signal? So that was the hypothesis we tested, and that is what we showed that, in fact, that is successful. So what we proposed was that, we have the standard model, and then now we also bring, we also bring the intermediate layers also closer together. It's a special mathematical loss function that we developed, nothing too fancy, mean squared error based, and also there's another one which is based on the Barlow approach, which is covariance. It's like bringing the covariance matrix closer to identity matrix. That will also make these representations close in their space. We tested both of these, and then in the context of chest X-ray, ophthalmology, and histopathology, which you can see the data sets here. And then our goal was to show that if your labeled data set is smaller and smaller, would you leverage more if your pre-training approach had been more successful? Okay, would you be able to get more mileage out of your data set, out of your labeled data set with better pre-training? Basically, the hypothesis is that by doing this approach, you actually eventually pre-train better models. Those better models are already good features for your tasks. And then we also, something I love about this paper is we actually evaluated these features through various objective ways. It's always very hard to evaluate how good something is. So objective evaluation of like the features themselves, not just through the performance, an AUC at the downstream test, but actually throughout via various processes that are all objective was our goal, which you can see some of these approaches. I won't have too much time to go into them, but I encourage you to have a look at this. They're based on some metrics to show that, I guess I can summarize them, the results, we kind of go faster. So first thing is, if your model is good enough for your task, we hypothesize that you don't need to change those features too much when you fine-tune it for the task, right? So we compare the features similarity before and after fine-tuning. The hypothesis is that our approach gives you a better starting point, meaning that you don't have to change them as much after fine-tuning, right? So that's kind of the first approach, and we showed that indeed that is true. Other approaches were like layer-wise pre-training. Again, our hypothesis is since intermediate layers become more robust, actually good features even earlier in the network are learned. And that's the core of what we showed. I won't dig into all of the results, but indeed in series datasets, we showed that especially with smaller data, but in general, with the smaller labeled data, this hypothesis indeed is true. Okay, so intermediate layers will lead you to better foundation models up front, like focusing on them. So this is better feature reuse, which I told you before and after fine-tuning. Like the model that was what we proposed, the learning approach actually improves the feature reuse, meaning that we don't have to change them too much to be able to achieve good performances. And then better features are learned earlier in the network, as I said. So you can, if you actually do explanation a lot of times, you can see there's a lot of noise in the early layers still, right? So that means that we still have room to improve those features in the early layers. And our approach is one tiny step towards that, but that direction is very good opportunity. Now, I'll be happy to discuss more on this one. That was a NeurIPS paper. And then this other one is also an application of self-supervised learning. And this one is in the deep learning for medical imaging conference. So this one, let me tell you a little bit more. It's a collaboration I have with my amazing students and collaborators. It's about specific type of lung cancer, squamous cell, which at the moment doesn't actually have a biomarker. When you're diagnosed with that, it's more common in smokers, and it's a part of our lung tissue that I guess if it gets damaged a lot over smoking or various reasons, maybe genetic, they become cancerous. They look very dense. Technically, this feature, this type of cancer is in this tissue that's very dense, and at the moment, there's not really, pathologists don't have a marker for which one looks better or worse in terms of prognosis. So that's a real medical problem that we started with. And now, how do we address that? In histopathology, you have, the challenge with histopathology is each data point is very large, 10,000 by 10,000 pixels, okay? And the way we process them is by patches, like it won't fit in any network. So you normally turn them into like 300 by 300 patches, and then you somehow aggregate the results across these patches. That's how histopathology works. I think I will just have high-level results here, so I'll just give you the overview of what we do in histopathology. So a lot of times when you do cancer subtyping, you can actually propagate the label of the whole slide to the patches, and it's okay. A lot of papers that do subtyping of cancer from histopathology, this propagation of labels, this assumption that, okay, if I have this subtype, every patch that I see is probably this subtype, this assumption is okay. But then when you start to look into survival models, patient-level models, suddenly it's not really a good assumption, and the prognosis depends on special types of cancer, like cancer tissues and subtypes. So you no longer, it's not a good assumption to propagate, okay, this patient died, this patient had a recurrence within some year, this patient didn't. If you apply that, your performances are really poor. So that's one problem with supervised learning in this setting. And self-supervised learning at least does most of the training without relying on the labels. So that is a good choice for learning. And then also, in general, you aggregate the signals at the patient level in histopathology. Histopathology datasets at the moment, especially the large ones, are coming from TCGA, which is a initiative, and there are like 1,000 something patients. It's not a lot of data. And by the way, everything I said about healthcare, so pathology guys had been really lagging behind because they are still living in an analog world where they archive their slides on a glass tissue. They don't digitize them. Okay, so that field is funny because there's so much opportunity. The models are really good, but their data world is a little bit funny still. For example, I can say that NYU just got a massive contract with Philips to switch to digital pathology 2 years from now. Okay, so NYU is one of the early ones to do that. They're going to scan all of these amazing datasets, but so far everything we could do was with publicly available datasets with TCGA, which you can Google. It's a good resource for histopathology images. So anyway, we focus on TCGA. We have like 1,000 something patients with squamous cell lung cancer. What can we do? We want to learn survival models because this is a hard problem, and also we want it to be interpretable. So what we did was that let me see if I have the methods here. So we first apply self-supervised learning. Let me quickly go a little bit forward. The self-supervised learning, the little trick is there's some problem in histopathology called batch effect, meaning that depending on how the technician, how much staining material they put, your image overall could be darker or lighter. And if you don't think about anything, you just throw your patches into your standard, self-supervised approach, you're gonna learn with higher probability the similarity, whether or not two patches belong to the same slide, which is batch effect. Okay, it's a well-known problem in histopathology. Naive approaches will fail. So what we proposed was that we actually sample image patches when we put it in a constructive learning according to where the patch came from in the slide, to try to make sure that we have enough patches from the same slide in the model to make the model's job harder, to be able to differentiate whether or not these two are augmentations. If you don't do that, like if you have, with very high probability, if you just naively sample in a batch that will be undergoing this contrastive learning, you're going to have, a lot of different background color already in that batch. So you're going to have really dark one here, and then you're from like one slide and a very light one somewhere else. So when you augment the image and ask the model, okay, which, this augmentation compared to other images in the patch that we just randomly sampled from different patients, which one is it? The basic properties of that image is already so close, okay, and compared to all the other slides that came and they look different through batch effect. So as a result of that, your model just learns, it's a very easy job for a model, just learns, okay, I just look at the color amount and I can answer correctly. Okay, so by ensuring that you have enough slides, you have enough patches from the same slide, you make the job harder because now the network has to look at the shapes and morphology to be able to answer that. That's a high level of the approach. So that's kind of what we did. We made sure that, you can see here like two slides. So when it's so much darker, it's not because the cancer is different, it's just because the technician used different amount of staining. That's very common in this setting, so you have to think about that. So what you do is normally you make sure that, we propose that you make sure that you have different slides from different patches from the same slide into your self-supervised setting. In that case, the model actually needs to be able to, tell is the augmentation of this guy different from like these patches or not. It's a harder job. It leads to better models. Now, as a result of that, we We tested it on TCGA dataset, and there's another publicly available dataset which we can also evaluate on, and we showed that the performances are much better. It's the first time we actually have a good model for this specific cancer. So there's not a lot of baselines, but we compared it to other approaches as well. And then you can, for example, here it's easier to see in terms of like the survival curves. What is available today is pathology stage, which is, okay, how does the nucleus look, how dense they are, stuff like this. That's a overall metric. That's the state of the art. That's what's there. If you use self-supervised learning, you can actually see that there is some good separation on nested held-out setting. So we are trying to be rigorous with our data set and evaluation. We split the data in 3 ways, and we do it in a nested way, multiple rounds. And the entire process is redone each round to make sure that the approach is helpful, right? So anyway, so the result shows that, okay, yeah, we can actually separate, there is a good performance in terms of separating patients who do have a recurrence and metastasis versus those who do not. Now, our focus is interpretability here, which is very hard. We were talking about it. When you have self-supervised learning, it's not problem-specific yet. So how do you make sure there's interpretability here? This was one approach we tried, which is that when I explained to you that we do self-supervised learning, all of these things, okay, so that's only the pre-training stage of it, okay? And then what we do is we cluster these representations. We just cluster them. We don't care about the application. We cluster in the representation space. We use Gaussian mixture model to cluster them. And then each slide now becomes how much of each of your clusters, which is presumably mean histopathological patterns, okay? How much of it is represented in each slide? So then the survival model, which is a Cox regression model, you can Google all of these, all are basic like linear kind of survival models, they operate on the clustered representation that came out of histopathology. As a result of that, we think that there is some explainability here. So let me show you. So these are, for example, we evaluated quite a bit with our collaborators, see what they can see in these clusters. And it's very subjective still, and I don't like the subjectivity part of it. We're working towards making it more objective. But these are some clusters that emerge that our pathologists thought that, okay, yeah, I see these general patterns in terms of the high-risk clusters. Okay, so you can kind of slowly start to move towards discovery, basically, which is what I love a lot, and it's really hard problem. And then additional high-risk clusters. They're all very interesting. There's a lot of data in here. What we will do next is to try to objectively describe these slides through a lot of terminology that's there. Okay, like infiltration of immune cells. You can actually measure that. Okay, so we can slowly try to say, okay, we have our clusters. Now try to explain them through other descriptive methods that are all automatic instead of like being very subjective. So that's at the high level our approach to imaging. I'll be very fast now. We're still working on all of this. Now, sorry, let me get some tea. So the next approach is electronic health records. Just change gears. Our lab is poor students. They have to handle so many different problems because our data is multimodal and we have to deal with that. So electronic health records, if you remember, I told you, these are like a lot of CSV files. Okay, we have like diagnosis CSV files, we have medications, we have procedures, demographics. These are the easy ones to de-identify, but we have a lot more which we haven't even pooled. There's the vital signs, there's like the visits, etc., which we don't even talk about. Okay, so at the core of it, if you look at them, it's like almost 500,000 variables. If you just say one hot encoding, what happened, yes, no, if you just list everything that you could possibly know at every time point, that could be very high dimensional, okay? Now, the problem is that I guess there's problem and opportunity. These variables are correlated. When you see a diabetes patient, you can probably adjust your what you think about them they might be a little bit more, probably maybe a higher BMI. The probability is higher. We kind of know that. They probably are on some diabetes medications. So if we know one thing about them, we can kind of fill out the rest of the variables a little bit if they're missing, for example, right? So how do you leverage this information? How do you even learn these connections? These 500,000 variables, there is no ontology that connects all of these together. There's no manual way to do that. How do you do that? This graph structure. So that's the core of self-attention. At the core of it is a graph model, actually. So we initially have one paper. Let me show you this one, which is specifically focusing on learning the graph structure, okay, out of these ones. That was about a year or two after transformers, but our approach was based on graph attention network, which are siblings to transformers, okay? The approach is based on learning self-attending to the nodes among what you see. Let me go back a little bit. Okay. You self-attend to the nodes that you observe, and then through that you learn the graph structure. And then after this graph structure, like a couple of layers of this, you update the representation of every disease that you have, even if it's missing. You kind of update it, and now you know a little bit more that it's there. And then you can aggregate this graph information and connect the classification head on top of it, basically classify this graph. Okay, that's one approach at the high level. Now, transformers are siblings to that. They have extra layers in between that actually makes the learning more robust. They have like residual connections, they have some projection connections. Initially, I was like, okay, what's the difference? But technically, engineering-wise, these things matter. So we actually moved now towards transformer architectures, which is more mature in terms of the engineering aspects of it. At the core of it, we are still learning the graph structure across all of our tokens, and we are actually using masked token generation. For example, you can kind of mask certain tokens, and then you ask the network to predict that the disease existed. You can also, in the original transformer paper, you also have some kind of temporal prediction where you have one half of the segment of the patient timeline, and then you want to predict the second half of their timeline. Okay, that's next segment prediction. In natural language, it's called next sentence prediction. These are all losses that are good. Based on the research, majority of the learning actually is from the masked prediction. That's what we know. But anyway, we apply for both of them. And then we have a study now. We have built the foundation model. We apply it to the same task that we applied on the graph neural network approach, which is dementia early detection. But that said, the foundation model is general purpose. So we also had a study for pancreatic cancer early detection, which that was in parallel to developing the foundation model. And now that we have the foundation model, we also apply it to the pancreatic cancer prediction. I'll just quickly go over this. The task is predicting dementia. Defining dementia is like this. That's really like if you work with EHR data, that's how you can usually define some diseases from your EHR data. And then you build some models, and so after the foundation model has been pre-trained through this loss functions, masked token prediction and next segment prediction, you fine-tune it for the task. It's a very hard task, early detection, but you can perform well. Okay, decent AUCs. So that has been the basis of a randomized clinical trial that we are proposing. Okay, in 2 years from now, we will click on this randomized trial where we'll test some centers in Brooklyn to see if AI can actually be useful in early detection for especially underserved populations. Okay, so we have two funded studies. One of them is actually applying this transformer model in real clinical setting. It's very exciting. And it's bigger project. And then this other one is about methodological approaches, about fair self-supervised learning when you have multimodality. I'll just quickly go on the fairness side and just basically wrap up. So there are a lot of fairness definitions as we talked about. There's no agreement. What is fair? Okay? We start with one thing in our setting, which is concern to me, which is good performance across all subcohorts. And I'm interested in good foundation models. When I open source a foundation model based on EHR or MRI or other modalities, I want it to be good enough for different smaller institutions, even if their population is different. So that problem is fairness. During SSL, it's not as tackled as other fairness problems. So as I mentioned to you, maybe you remember from the diversity in AI, so in this setting, your data is unlabeled. In advance, first of all, you may not even know gender, race about them. You may just have a lot of MRIs or a lot of EHR data without really knowing what's the gender, what's the race. You may not know which variables are the cause of unfair problem. So a lot of standard approaches manually engineer based on known variables, and they fix the approach to some extent, they correct it. We cannot do this. Also, what would you do if there is interactions between the elements? So a lot of these problems are untackled. Our approach is completely not relying on any labeled information to try to improve the fairness. It's a hard problem. So the way we tackle it is we know that during the learning, if there is a sub-cohorts that have different base rates for certain conditions, for example, let's say older patients, okay, that generally have more diseases than younger patients. One possibility could be that the model learns old means sick. I'm just going to kind of associate age with, virus sickness, and I don't worry about within the old patients, which ones are healthy or not. Most of them are sick anyway. Let's just learn that old means sick, right? That's called shortcut learning. It's common in learning when you have some sub-cohorts that have different base rates. How do you avoid this? This is kind of what we try to tackle in an unsupervised way. We define, this is technical, I will skip most of it, but we define correlation aligned, meaning patients who are old, for example, patients who are old and sick, okay? And then correlation conflict is the subset in the old patients who are actually healthy, okay? And the goal of learning a good foundation model is that you have good features for all of the subcohorts, young and old, meaning that you learn good features among the elderly to be able to differentiate sick and healthy, for example, right? So that's kind of the high level of what correlation aligned and correlation conflict means. We discovered, I will skip this, that's just a reminder of how contrastive works. We discovered that when you track these two subcohorts, correlation aligned and correlation conflicting patients, like old and healthy, the performance is lower, okay, and during the training. So you can detect these subsets of samples in your data set that somehow are not learned as much. Even if we don't know who is old or young, we actually track their learning metric, and we define the learning metric based on contrastive setting, okay? I won't have time to go into it, but I will be happy to answer questions. We can detect it throughout the learning process, and then by leveraging this, as we detect it, we oversample these subsets that somehow are worse. And then oversample them, we emphasize them during the training, and as a result, the performance, the learning quality improves for all of these. It may be a bias problem, it may be a shortcut problem. In fact, it is a good solution for a lot of problems. What we do, but we show that indeed, in terms of fairness across like performance on various data sets, some of them are medical data sets, and then some of them are general data sets in AI, we can show that these performances on biased minority groups do improve quite significantly. Okay, so you can see this is like a synthetic data set. This is a mimic data set on all of those, especially like old and, let's say classifying normal chest X-ray among the elderly versus abnormal. We improve the performance by these approaches. So I'm really excited about this. This approach was developed for imaging, but we have EHR foundation models, which is also very rich domain, ripe for fairness. And that's what we are going to do next. This paper is under review. That's all. My lab has focused on all these years to building representations on separate modalities, but now our funding and also our next level is to combine them in a multimodal setting. So what we focus on is we have representations for EHR, let's say foundation model transformer. We have representations for histopathology. We have, let's say, also MRIs, etc., maybe genomics. How do you combine them? At the moment, the state of the art is now moving towards basically one architecture to rule them all. Everything transformer, you just throw in all of the tokens at the same time. You do mask pre-training, and that's the basis for Google's Palm multimodal Palm method, which you may have met Palm, for example, which you may have heard about. The basis architecture is the last one, where kind of just at the very token level, you map everything to tokens. The rest of it is a massive transformer that trains everything. It's very interesting. Anyway, we are not, I'm going to skip these ones. So that's all I have to say, I guess, in terms of diverse settings that are ripe for research. Foundation model, in my mind, is the way for medicine. And as you heard, there's a lot of interesting developments there. I encourage you to learn more about it. And yeah, they actually solve a lot of unsolved problems. So that's what I'm excited about. Thank you so much.